So let's start with the first example with this section, which is, first of all, you see the examples, we need to show that V is an eigenvector of A. And then you're going to find the corresponding eigenvalue. So your goal here, just go ahead and find the corresponding eigenvalue. If you find the corresponding eigenvalue, that means V is going to be a vector for A. So let's check how we're going to find that. Here's the rule. Remember the rule, it says AX equal lambda X. So here we're not going to work with the vector X, we're going to work with the vector V. So AV equal lambda V. That means the matrix A is equal -1, 1, 2, 0, -1, 1, and 2, 0. And the vector is 1, 2. So I'm going to prove that, and I'm going to find the eigenvalue. So AV, that means here is A, times the vector V, which is 1, 2, equal lambda, and here is the V. So we need to solve this one. So multiply these two matrices. We can multiply because this is times 2 times 2. This is 2 times 1. That means we can do the multiplication. So in this case, -1 times 1 is going to be -1. 1 times 2 is going to be 2. And 2 times 1 is going to be 2. 0 times 2 is going to be 0. This is 1 is going to be equal lambda, and here is 1, 2. In this case, we're going to find two equations. You can say -1 plus 2 is going to be 1. 2 plus 0 is going to be 2. And everything here is equal lambda and 1, 2. That means 1 equal lambda and 2 equal 2 lambda. In this case, lambda is going to be also equal 1. So here is the value of lambda. You don't have to get different because it's only 1 lambda. So that means V is an eigenvector for the matrix A. Matrix A, why? Because we found the lambda equal 1. If you got two different lambda without doing any mistakes, that means V is not an eigenvector for the matrix A. And you will see we're going to do exactly the same thing with example 2. But now we have 3 times the 3 matrix. So the second one, we have the matrix A equal 0, 1, -1, and 1, 1, 7, and 1, 8, 0, and the vector V equal -8, 1, 1. So we're going to do the same thing. We're going to say A V equal lambda V. So here is the matrix A, which is 0, 1, -1, 1, 1, 7, 1, 8, 0, times the vector V, which is -8, 1, 1, and equal lambda with the matrix -8, 1, 1. So multiply these two matrices. We can do the multiplication because 3 times 3, 3 times 1. That means the result is going to be 3 times 1. 3 rows, 1 column. So the first thing, when I'm going to do 0 times -8 is 0. 1 times 1, so plus 1. -1 times 1 is going to be -1. 1 times -8 is going to be -8. 1 times 1 is going to be plus 1. 7 times 1 is going to be plus 7. 1 times -8 is going to be -8. 8 times 1 is going to be 8. 0 times 1 is going to be 0. So this is the multiplication, and everything here equal lambda with -8, 1, 1. Now, if you add these, you're going to get 0, 0, 0 equal lambda. Here is -8, 1, 1. In this case, lambda is going to be equal 0. Because 0 equal lambda times -8 divided by -8, lambda is going to be 0. 0 equal lambda and 0 equal lambda. So we found the lambda equals 0. That's mean A times V equal the lambda times V. So if you multiply A times V, the result is going to be 0, 0, 0. Put down the lambda here times V, also the result 0. That means we have two equal sides. Then our lambda here with this example is going to be 0. So we're just going to put 0 here. That's how we're going to prove this vector or any vector is an eigenvector from this matrix. You have to find a lambda. That means this equation is going to be right. This is for the first one, and the second one, the same thing. Is an eigenvalue. You can do the same steps, or we're going to find eigenvector right away. Find the eigenvector V. But to prove that, show that lambda is an eigenvalue of A, you have to do the same steps here. And then you're going to find the eigenvector. So I'm not going to do the same steps. I'm going to go ahead and find the eigenvector right away, which is a vector V, a vector X. It's up to you what you're going to call it. So what we're going to use here, number 3, I have A equal 0, 6, -1, 7. And lambda equal 1. So to find the eigenvector, I'm going to use the equations. If you check the slides, A minus lambda I times the vector, let's say the vector V with xy equals 0, or x1, x2. Then in this one, this is everything times the vector V. I'm going to let here V equal x1, x2. That's mean on this one, on this side is going, we need to find the eigenvector. So always do the same steps. That's mean the matrix A, which is 0, 6, -1, 7, minus lambda. We already know how much the lambda, which is 1. So I'm going to plug in 1 here times the identity matrix, and everything here times the vector x1, x2, which is the vector V equals 0. Let's simplify this side. We're going to get this matrix, because here is 1. It's not going to do any change with the identity matrix. So 0 minus 1 times 1 is going to be -1 here. 6 minus 0 is going to be 6. Now -1 minus 0 is going to be -1. 7 minus 1 is going to be 6. And this one is going to be times x1, x2 equals 0. Now I'm going to take this matrix and simplify it, or it's up to you. You can work on this system to find x1 and x2. What I'm going to do, you can work on this system because it's a system with 2 times 2 matrix. It's easier to find 2 equations and solve it. But what I'm going to do, I'm going to take this matrix and reduce it. I use in row echelon form. So I'm going to say R or -R2, or you're going to say R2 equal negative 1 times R1 plus R2. Again, it's up to you how you're going to work on. You can work on this system or you're going to reduce it. But what about if you have 3 times 3 matrix, 4 times 4 matrix, 5 times 5 is going to be different. You can't work on these equations. That's why we're going to use the reduced row echelon form. So here is the first row is going to be the same. And the second one, negative 1 times negative 1, 1 plus negative 1 is going to be 0. This is going to be 0, 0. That's mean in this case, if you multiply the reduced with x1, x2, let's type here x1, x2 equals 0. That means it's going to be negative x1 plus 6x2 is going to be 0. That means x1 is going to be 6x2. Here, we're going to let x2 equal t. So in this case, x1 is going to be 6t. So the vector v is going to be x1 is 6t and x2 is going to be t. Here, I'm going to let t equal 1. So I'm going to get this vector v equal 6 and 1. This is the eigenvector. Of course, you're going to get more than one eigenvector. It depends about t. That's why, let's do a simple graph here. This vector is 6, 1 when t equal 1. 1, and here is 6. Let's do 4, 5, 6. So here is this vector. If you take in t equal negative 1 is going to be negative 6 and negative 1. Negative 6, which is 1, 2, 3, 4, 5, 6. Negative 6 and negative 1 here, so it's going to be here. If you take another t, is going to be here. That's why it's called span. You see what will happen? Every time you take in t, is going to be different vector. That's what it's called span. So eigenspace is the collection of all these vectors. That's why we're going to say eigenspace for the lambda equal 1 is going to be span for all these vectors. And I'm going to say when t equal 1, so I'm going to say just for the vector I have 6, 1. That means span for this one. If you take another t, is going to be span for the new vector and keep going. So every time when you take in t, is going to be different vector. If you let t equal 1, here is the vector. If you let t equal negative 1, you're going to get this vector. If you take t equal 2, it's going to be different vector and a little bit longer. So that's why it's called span. So we're going to check that here. 6 and 1. Here we go. So example 5, don't confuse yourself about what they're saying here. You're going to get 2 lambda, keep in your mind, 2 lambda here. Each lambda, there is an eigenspace, and you will see the eigenvector for the first lambda, its reflection on the eigenvector on the second one. It's going to be reflected over x-axis. Let's check that. We have the matrix A. The matrix A equal, so this is example 5. The matrix A equal 1, 0, 0, 1. Is that right? No. 0, 1, 0, 1, 1, 0. Now in this, the first step, if you look at this example, there is no eigenvector. So I need to find the eigenvector, the eigenvalue. Then from the eigenvalue, I can find the eigenvector. And from the eigenvector, I can locate the eigenspace. So I'm going to use, here's the important equations. Determinant to find the eigenvalue, A, determinant of A minus lambda I equals 0. Determinant of A is 0, 1, 1, 0 minus lambda times the identity matrix with 2 times 2, dimension 2 times 2 is 1, 0, 0, 1 equals 0. You have to practice on these examples because it's easy to do mistakes. So it's going to be the determinant of, I'm going to write down, now 0 minus lambda. 0 minus lambda. So lambda times 1, don't do the steps right away, because now we have easy numbers. But if you have different numbers, it's easy to do mistakes. 0 and negative lambda. So now I don't have to put negative sign here. And this one equals 0. Now it's going to be the determinant of, I'm doing these step by steps, 0 minus lambda. So here is negative lambda. 1 minus 0, here is 1. 1 minus 0, here is 1. And here is negative lambda. And this one equals 0. Now we're going to find the determinant for this one. That means negative lambda times negative lambda minus 1 times 1. And this one equals 0. It's going to be lambda squared minus 1 equals 0. That means lambda squared equal 1. Lambda is going to be plus or minus 1. So we have 2 lambda. We have the eigenvalue plus 1 and the eigenvalue negative 1. Then we need to find eigenvector for each one. So what I'm going to do, I'm going to say when lambda equal 1. I'm going to go back here and plug in lambda equal 1 without finding the determinant, because I need to find the eigenvector. So it's going to be negative 1, 1, 1, negative 1. I need to find the eigenvector, so I'm going to multiply by v equals 0. Let v equal x1, x2. So multiply by the vector v, it's mean negative 1, 1, 1, negative 1 times x1, x2 is going to be 0. It's up to you. You want to reduce this one by using row echelon form, or you want to work as a system, but I prefer to keep practicing on reduced row echelon form, because if you have different dimensions, it's going to be different. So I'm going to take this matrix and reduce it. So I'm going to say 1, negative 1, and here is negative 1. With the 0, we're just going to add R1 plus R2. For the R2, R1 plus R2. So it's going to be negative 1, and here is 1, 0. This one is going to be 0, 0, 0. That means x1, negative x1 plus x2 is going to be 0. It means x1 is going to be equal x2. So in this case, we're going to let x2 equal 1, or equal t. That means x1 also equal t. So the vector v is going to be t and t. Let t equal 1. So the vector v is going to be 1, 1. On the same time, the eigenspace when lambda equal 1 is going to be span for the vector 1, 1. So we're done. This is only when we have lambda equal 1. So we're going to plug in here when lambda equal the first, here is the first lambda. It doesn't mean lambda equal 1. 1, the eigenspace is 1 and 1. Now let's go, they say the smaller lambda value. So this means that we have to put -1 over there. And here's the large. So here the other lambda, which is -1, and now I need to find the eigenspace, eigenvector and eigenspace. So when lambda equal -1, we're gonna plug in here to find the eigenvector. So it's going to be negative lambda, that's mean -1, so it's going to be 1. And here the second one is going to be 1. The third one is going to be 1 and 1 times the vector v going to be equal 0. So what I'm going to do now, I'm going to say 1, 1, 1, 1 times x1, x2 equals 0. So next step, we're going to use the reduced row echelon form to find the value of x1, x2, and this one here. So in this case, we're going to say -1 times and a plus, minus times and a plus. So I'm going to say R2 is going to be -1 times R1 plus R2. And this one is going to be 1, 1, 0, and 0, 0, 0. That's mean x1 plus x2 is going to be equal 0. In this case, x1 is going to be negative x2. Let x2 equal t. So x1 is going to be negative t. So v is going to be x1, x2, which is equal x1 is negative t and x2 is t. Let t equal 1, so v is going to be equal -1 and 1. So this is the eigenvector. Now to find the eigenspace when lambda is -1 is going to be equal span to this vector -1 and 1. Now let's check. If we do a simple graph, and let's check these two eigenvalue and eigenvectors. So the first, let me change this one first. It's -1 and 1. If you look, let's graph the first vector. We got it 1, 1. The first vector, eigenvector got 1, 1. So it's going to be here is 1, and let's say here is 1. So here is the first vector. Let's do it here. This is 1, and here is 1. So here is the first vector. Okay. The second vector is -1. This is -1 and 1. So here is the second vector is -1 and 1. That's why they're telling you reflection in the line y equal x. This one is reflected on here, on the y coordinate. So that's why they're telling you. So don't confuse yourself when I'm telling you reflection. How are you going to work on it? No, find the eigenvectors and you will see this vector is reflect over this vector. If you took t equal 2, that means you're going to take t equal 2 with the first to find the vector, and you're going to take the t with the second one to find the vector, and it's going to be the same thing. This one reflect on this one, and keep going. That's it for this example. So example 6, a equal 1, 0, 0, 0. We're going to do exactly the same steps, and you will see two vectors. Okay. So now we're going to use the equations to find the eigenvalue determinant of a minus lambda I equals 0. That's mean determinant of 1, 0, 0, 0 minus, I'm going to multiply lambda right away with the identity matrix equals 0. That's mean is going to be determinant of the matrix 1 minus lambda and 0, and here is 0, and here is going to be negative lambda, and everything equals 0. So to find the determinant for this one is going to be 1 minus lambda times negative lambda equals 0. Then distribute. So it's going to be negative lambda plus lambda square. And you don't have to distribute because the same thing, you're going to factor lambda on the left is going to be negative lambda plus 1. Negative 1 plus lambda equals 0. That means we have lambda equals 0. And the second one is negative 1 plus lambda equals 0. It means lambda is going to be equal 1. So we have lambda equals 0 and lambda equal 1. So in this case, we have to start with one of these. Let's start with the smallest one when lambda equals 0. I'm going to plug in this one here. It's the easiest one. You don't have to go back to the beginning. Plug in here, so it's going to be 1 minus 0, it's going to be 1. And here is 0, 0, 0. Times v equals 0. That means 1, 0, and 0, 0 times x1, x2 equals 0. Again, we have to assume that and v equal x1 and x2. So we don't have to simplify this one because you can't. You just have x1 equals 0. So even if you reduce it, it's not going to be reduced. So we just have x1 is going to be equal 0. That means x2 equal any number. So let x2 equal t, or equal 1. Let's do it 1. That means the vector v, which is equal x1, x2, equal x1 is 0, x2 is 1. Eigenspace when lambda equals 0 is going to be span to the 0, 1. So on the first one, the smallest eigenvalue is 0, the eigenspace span to the 0, 1. For the second one, when lambda equal 1, we're going to do the same thing. We're going to plug in 1 here. So the matrix is going to be 1 minus 1, 0, and here is 0, 0, negative 1, times the vector v equals 0. That's mean 0, 0, 0, negative 1, times x1, x2 equals 0. Again, you don't have to simplify it, but we found that x2 is equal 0. That's mean x1 equal any number. So the vector is going to be x1, x2, which is mean equal x1 is any number. Let's x1 equal 1, 1, and x2 is 0. And again, the eigenspace when lambda equal 1 is going to be span to the vector 1, 0. Now let's do a simple graph between this vector and this one. The first vector is 0, 1. X is 0, y is 1. Let's say here is the first vector. The second vector is 1, 0. That means x is 1, y is 0. So if you look here, it says this is v1, and let's say this is v2. So you can know v2. There's v1. So if you look here, it says a projection onto the x-axis. That's mean this one project on the x-axis. Project on the x-axis. That's why I'm telling you, don't confuse yourself when they're telling you project or reflect. Go ahead, just do the eigenvalue and the eigenvector. Find the eigenvalue, eigenvector, and eigenspace. And that's what it's going to be. When you grab the vectors, the eigenvectors, you will see it's a project or reflect, or like the next example is stretch. So it's going to be a little bit longer with the next example by the factor, horizontally by the factor 8. They do exactly the same thing. And when you graph the first vector and the second vector, you will see it's going to be stretched horizontally. That means the first vector, this is just a hint. That's mean, for example, when you graph the first vector, let's say we got the first vector like this. The second vector, you're going to stretch horizontally. That means you hold the vector and stretch horizontally. So maybe it's going to be like this when you graph it. Okay? Talking about example 7. Because I just like on the homework or on the test, you can't tell because now I'm just looking here. I have only one lambda. That's why I say, oh, maybe there is something wrong with this example, because how are we gonna find it's a counterclockwise rotation? You have to graph more than one vector. So let's check how we're gonna do exactly the same steps for this example. And the matrix A equal 0, 1, and negative 1, 0. So I'm going to do exactly the same thing. I'm going to find the determinant, and here I'm going to let the vector v equal x1, x2. That's mean determinant of A minus lambda I is going to be 0. So determinant of the matrix A, 0, -1, 1, 0, minus. I'm going to distribute the lambda on the identity matrix, and everything equals 0. So let's simplify this one. That means the determinant of, here's the matrix, 0 minus lambda, and -1, and here 1 minus 0, and here is going to be negative lambda, equal 0. Find the determinant for this matrix is going to be negative lambda times negative lambda plus 1. Here's the thing. -1, because minus -1 times 1 is going to be plus 1. So that's why lambda times lambda is going to be lambda squared equal or plus 1 equals 0. That means lambda squared equal -1. If you take the square root for both sides, lambda is going to be plus or minus square root of 1 is going to be I. Because square root, that means this is complex number. We can't work with the complex number. So that's why you're going to say DNE or DEN. DNE. So I'm going to type on both D and E. And here, when I'm going to type D and E, both, I don't know. D and E, D and E. Yep, that's it for this one. The same thing with this example, and you will see we're going to graph it. We're going to graph these. So this is really nice example. So, but here's the matrix 3, 5, 8, 0. Yeah, I can check that. So for this example, you see what we did? Exactly the same steps. Determinant, plug in everything. Then here we get the quadratic. You will see on the next section, or section 4.3, we're gonna get a lambda, a function with a lambda equal 5 to the exponent 5. So we have to use the scientific division to find the how many lambda do we have. So it depends about, this is easier because quadratic, go ahead factor. We found 2 lambda, lambda equal 8, and lambda equal -5. When lambda equal -5, plug in, use reduce or echelon form. Here we got, here is the equation 8x1 plus 5x2. Then solve it for each variable, for x1 or x2, it doesn't matter. So x1 is going to be -8 over 5, x2. Let x2 equal 5. Again, you can assume any number. So x1 is going to be -8. I just need to cancel the fraction to get only numbers, because these numbers is easier to graph. Now, the next step, when lambda equal 8. So I'm going to do the same thing, but now lambda equal 8. So when lambda equal 8, I'm going to plug in the characteristic. So it's going to be 3 minus 8, that's mean -5. And here is 5, 8, -8. -5 here is going to be 5, and here is 8, and here is -8. Times v equals 0. So we're going to do exactly the same thing. Let's put this one here. And here, what we're gonna do, we have to reduce it now. So I'm gonna say this is -5, 5, and 8, -8 times x1, x2 is going to be 0. Then I'm gonna use -5, 5, 8, -8 with the zeros. Then to reduce to the raw echelon form. So the first step, I need to convert this one to 0, sorry, to 1. So R1 is going to be -5, which is the old one, divided by -5. So the first matrix is going to be, this is going to be 1, and divide by -5, so -1, and keep the zeros. Then here is 8, -8. Then here is the new matrix, 1, -1, 8, -8, 0, 0. Now what I'm going to do, I'm going to say R2 is going to be 8, or -8, times R1 plus R2. So here is 1, -1. So -8 times a plus is going to be 0. -8 times is going to be 8. Plus -8 is going to be 0. That's mean x1 minus x2 is going to be 0. In this case, x1 equal x2. Let x2 equal 1. So x1 is going to be 1. So the vector is going to be x1, x2, which is equal 1, 1. So the vector is 1, 1. That means eigenspace when lambda equal 8 is going to be span 1, 1. That's it for this example. We can check that. So just the eigenspace 1 and 1. Yes. Then let's check which one is going to be the right one. Try to graph it. Try to graph it before you look to the option. So the first eigenvalue, you get -8 and 5. So 1, 2, 3, 4, 5, 6, 7, 8, and -8 and 5. Yes. 1, 2, 3, 4, 5. That mean is going to be here. Here's the first vector. This one we can say when ax equal the lambda is 8x, because the first, the 5, the first lambda is when, -5x. So ax equal -5x. You get this vector. The second one is 1, 1. Here is 1, 1. So this vector is ax equal 1x. I have to choose like this one. Let's see which one. See 2. This is wrong because the lambda is 2. And this one is not. Let's see which one. We got this vector is -5 on this side. So could it be this one? Because -5. What about here? They didn't mention here how much this goes 1, 2, 3, 4, 5. Mm-hmm. 4. Let's see this one. It says now we have to get -5. The first vector is -8 and 5. Oh, not this one. I can choose -8 and 5. That's mean should be goes to the different. Oh, this is, I know I choose the wrong one. Negative, and the second one is supposed to be 8. So here's the wrong thing. We got the first one is wrong because when I solve it for the first one, for x1, that means it's going to be -5 over 8. So I'm going to do the same thing. I'm going to multiply this one by 8. X2 is 8. So x1 is going to be -5. Yeah, that's made more sense. That means x1 is -5 and x2 is 8. -5 and 8. So let's make more sense now. Let's change this one. It's going to be -5 and here is going to be 8. Let's check and then I'm gonna find. So when you graph it, it's going to be -5 and 8. 5, 6, 7, 8 is going to be 1, 2, 3, 4, 5, and 8 is going to be here. Not this one. So like this.